this week, when it shows up on the screen, just click on that one, show that. Okay. Yeah, so this week we're covering the chapter 3 content, okay, which obviously was made available on Monday. Well, you don't have to look through it because we're just running it as a regular lecture. So, in chapter 3, we'll cover the learning objectives of the chapter, and then we're going to look at very much focus around 2-degree of freedom systems, and then we'll look at 3-degree of freedom systems at the end. The focus of this, it should be content that you probably covered last year with Gary, although we've got a few more tricks and coming plans with the content in here. But obviously the real relevance of this stuff is that next week when we talk about forces on the vehicle, we're going to look at what's known as the car model, which in essence is a 2-degree of freedom system, because you've got a sprung mass and an unsprung mass on the ground, okay? And obviously we're using the skills that we're going to pick up in this session to cover that content, because it's the same. It's basically a specific type of 2-degree of freedom system with 2 natural frequencies and 2 mode shapes. And we're going to look at that, and then we're going to go to the lab on the Monday, the following Monday, and we're going to have a look at the rig that we've got in there that does that system. So that's the plan for the next week or so. But before I do that, I need to cover this stuff, which is what the point is. So for this chapter, we need to work out how to write the equations of motion for linear multiple degree of freedom system using the matrix form, and that's where the trick is. In the past with Gary's stuff, you had to cover, you had to get the stuff in the beginning, use the second law, write out all the forces, and then rearrange it. I've got a very quick method to do that, so we'll cover that. Okay. Then you can determine the mechanical impedance matrix and take the determinant of it to work out natural frequencies for 2 and 3 degree of freedom systems. Okay, then I'll teach you how to do that by hand. Next week, that's when we're covering this stuff. I shall show you how MATLAB can do it, and then also work out the mode shapes for grounded and undergrounded 2-degree of freedom systems and ungrounded semi-definite systems. Okay. So some of these words may be familiar to you from last year when you were doing this sort of stuff with Gary. Okay, but we'll get there because we're enhancing all that. So here's the 2-degree of freedom system. So you can see that we sort of systems we were looking at previously, where there was just one mass, now we've got 2 masses, and they represent the 2 degrees of freedom system because they can move independently of each other. Okay. So we've got 2 degrees of freedom that we need to look at. So then obviously we've got a bunch of springs and dampers and forces being applied and this sort of stuff. Okay. So that's a generic system. Okay, depending on what there may be other specific things going on, but that's the generic system, and obviously you can then go through and apply Newton's second law. So if we take the first mass, the sum of all the forces equals mass times acceleration. So if we go back and look at the first mass, okay, so you can see that we've got on this mass we've got 2 springs, K1 and K2, okay, and K1 depends solely on x1, that motion of mass 1. Okay, K2, okay, it's between the 2 masses, so that depends upon the difference in displacement between x1 and x2. So you've got k1 times by x1, and k2 times by quantity x1 minus x2. And that's gives you the force on from the springs. Okay, they oppose motion, so they're always going to be negative. Okay, and the same with the damper. So we've got the damper C1, which is going to be dependent upon x1 dot. Okay, because dampers are viscous on velocity. And then this damper C2 is going to be on the difference of velocity between mass 1 and mass 2. So that's going to be x1 dot minus x2 dot. Okay. And again, it's negative because dampers oppose motion too. Okay. And so you can see that from the springs and the dampers, and then we've got this force that's acting in the same direction. So you've got the springs, the dampers, and the force all applying on mass 1. And they must sum up to equal mass times acceleration. So that's the one equation for mass 1. For mass 2, you repeat that process. So for mass 2, we've got K2, which is dependent upon the difference in displacement between x2 and x1. So it's K2 times x2 minus x1. And then we've got K3, which is entirely dependent upon the position of mass 2. Okay, so it's just K3, x2. And the same with the damper. So this is entirely dependent upon the velocity of mass 2, and this one is on the relative velocity between mass 2 and mass 1. Okay, and then also we've got another force. So you can do that. So here's the two masses. Sum of all the forces equals mass times acceleration. Okay, Newton's second law. So here are all the forces. So we've got the force that's being applied directly. You've got your damper, C1, which is just dependent upon the velocity of the first mass. C2 is between the masses, so you've got the relative velocity. Again, K1 is also dependent upon the displacement of the mass 1, and then K2 is on the relative displacement between the two masses. And then obviously what I've done here is I've stuck all the x terms on one side, okay, and the force on the other, and then you repeat that process for the second force, okay, so for the second mass. So it's straightforward level 1 dynamics, it's just lots of forces. And like I said, if you drew a three-body diagram or box and you labelled all the forces, you get these equations. Okay? What's complicated about these equations is they're coupled. Okay, so we've got equation for mass 1. Okay, has not only mass 1 bits in it. There's the acceleration, there's the velocity, and there's the displacement. But there's also, it depends upon what's happening to mass 2 as well. And you can see that in the equation. Look, there's a mass 2. What's this whole equation can be solved as long as you know what the velocity of mass 2 is, and likewise the displacement of mass 2. Okay, so they're coupled together. These equations. So to solve them, you've got to solve them simultaneously. And the cover, that's quite tricky. Okay, we use a computer for that process. Anyway, but like I said, we're not going to worry too much about that today. Okay, so that's Newton's second law, and obviously what you can do with that is you can stick them in matrix form. If you take this line, okay, and this line, you can put them in matrix form. Okay, so that's what this next slide is showing. It's stuck in them in matrix form. So we've got, take the first line, we've got m1 times by x1 double dot, okay, and then plus c1 times c2 times x1 dot minus c2 times x2. And k1 plus k2 times x1 minus k2 times x2 equals f1. Okay, that was the equation. So you can, like I said, by rearranging by rearranging the equations, you can put them in matrix form. And for any linear system, you'll be able to put them in this sort of format. Okay, where you've got n, which is your mass matrix, which is up there, times by x double dot, which is our acceleration. Then you've got your damping matrix times by x dot, which is your velocity, and then your stiffness matrix times by x, which is your displacement, equals the forces. Okay? So m in square brackets is the mass matrix, c in square brackets is the damping matrix, and k in square brackets is the stiffness matrix. Okay? F and x are the force and displacement vectors respectively, and clearly x dot is the velocity, and x double dot is acceleration. And any linear system, okay, we'll cover non-linear systems, well, we can't write like this. No, we won't. You can cover it, but any linear system will fall into that category. My son is joining us in the lecture because he's on half term already.
Lucky him.
I'll just remind him to stop thinking.
Just stop.
Right. Of the free oscillation, as we covered, there's no driven forces, and so obviously F1 and F2 will be 0. Now, there is a quick method to get those matrices straight away from the picture. Okay? The mass damping and stiffness matrices allow you to quickly arrive at the equation of motion of the system. Okay, so instead of getting through Newton's second law, which is prone to error, and we've got all those subscripts and superscripts, this is an easy way to do it. Okay, so matrices, they're all square matrices. So if you think about the number of rows and number of columns, they're all going to be the same. Okay, but what we're saying is that these are for all the positions where I'll talk about that. So for the mass matrix, basically when I say MII, okay, so these are all the positions down the diagonal, okay, down the middle of the matrix. So when you've got the first row, first column, second row, second column, third row, third column, and so on, okay, they're just going to be your masses. M1, M2, M3, M4, and so on. Okay? So you just position them down the diagonal. All the other elements of that matrix are 0. Okay, so if we go back to that matrix, there we are. So here we've got M1, M2 down the diagonal, everything else is 0. Like I said, if you have a 5 degree of freedom system, your masses will just run down the middle. Okay, all the other ones. That's easy. Okay. For the damping and the stiffness matrices, okay, for the diagonal positions, what you do is you add up the values of the dampers or the springs, okay, depending on whether you're working with stiffness or the damping matrix, linking that mass, okay, that first mass, to ground or to another mass. Okay, so it's connected to ground or to another mass, you add them up and you put them in that hole. Okay? So obviously for the first mass, you add up the springs connected to ground or to another mass and you just put that in that hole. And that's the diagonals. So first mass, second mass, third mass, first mass, second mass, third mass, down. And you do the same thing for the dampers. Okay, so again you add up the dampers connecting to ground and to another mass. Okay. For the off diagonals, okay, so we've now got I and J being different values because I didn't J. Okay, for the off diagonals. So first row, second column, and second row, first column. What you do is you add up the dampers connecting those masses together. So if we're saying first row, second column, that's between mass 1 and mass 2. Or likewise between second row, first column, that's also between mass 1 and mass 2. You add those up, those things connecting the masses to each other, and then you take the negative side in front of them. Okay? So on the diagonals, masses connecting M1 to ground or to another mass, and then I and J is where you're looking at the things between mass M, I and J, okay, where I is 1, 2, 3. Okay? And then you end up with your MC. Okay, they are symmetrical matrices. So if you do this method and you end up with something that's not symmetrical, symmetrical meaning around the diagonal they're the same thing, because obviously between mass 1 and mass 2 is the same thing as saying between mass 2 and mass 1. So there's going to be two elements that are the same. And they're diagonal matrices, or symmetrical matrices. If they're not symmetric, then obviously you've made a symptom. So I've got an example of that. So we've got this 2 degree freedom system up here. Okay, you've got springs and dampers and all sorts of things joining the thing. So what you do is you set up your mass matrix. Okay, M1, M2, 0 and 0. And that's multiplied by x1 double dot, x2 double dot. Okay? There's my damping, there's my mass matrix. Like I said, it's very straightforward. You just set up the masses down the diagonal. And so okay. Now we've got the damping matrix. So we can see that mass 1, there's only one damper connected to it. It's got a value of C. Okay? There's only one, look at mass 1, there's one damper and it's got a value of C. So I stick that in the diagonal. Okay? And let's look at mass 2. Then we've got 2 dampers connected to it, C and 2C. So you add them up and you've got 3C. Okay. Now for the off diagonals, we need to look at the dampers between the masses. So we ignore this one, because that's between ground, okay? But this one between mass 1 and mass 2. And so off the diagonal, we've got minus C here and minus C here. And that then equals x1 dot, x2 dot.
Sorry, I didn't catch that. What was the justification of negative C?
With the off diagonals, okay, you take the minus sum of the things that springs dampers between the masses.
Oh, okay, yes.
And here with first row, second column, the second row, first column, so it's between mass 1 and mass 2.
Oh, so you're taking away the difference.
Yeah, and if you had 3 masses, then you'd have a 3 by 3 matrix with first and second, first and third, and second and third. And likewise with the springs. So connected to mass 1, we've got K and 2K, so that's 3K in total. On the diagonal, Off the diagonal we've got minus 2k. And on the diagonal for the third mass, again we've got 3k. And that's times by displacement, x1 and x2. And then we've got the forces, F of t and F of t. So from the picture, we've gone straight to the matrix form of the so we didn't have to do Newton's second law. But they will give you, if you expanded them out, you'd end up with two equations, one for mass 1 and one for mass 2. That would be your Newton's second law. F of t. F of t, F of t. Okay. So the same force is being applied to both masses. Okay, so let's do this one then. So again, the mass matrix is simply M1 and M2. X1 double dot, X2 double dot. Damping, we've got, for mass 1 we've got 2C and C, so that's 3C. For the second mass it's 4C. And between the masses is minus C. And then for the third stiffness matrices, we've got 3K, minus 2K, minus 2K, 5K. X1, X2. There are no forces being applied because this is free vibration. So you've got 0 and 0. Okay? Okay, let's do this one quickly. So together, again, M1, M2, 0 and 0. X1 double dot, X2 double dot. So we've got just 2C connected to mass 1 and C connected to mass 2, but there's nothing between mass 1 and mass 2. So the damping matrix is uncoupled. X1 dot, X2 dot. Then we've got the stiffness matrix. So that's 4K, 4K, minus 3K, minus 3K. X1, X2. And there's only one force being applied to mass 1. Okay. And there's one more. For this one, M1, M2, X1 double dot and X2 double dot plus. So connected to mass 1 we've got C1 and C2. So you click on C1 and C2. But there's nothing connecting it to mass 2, so we click 0 and 0. For mass 2 there's no dampers, so that's also 0. And then for the stiffness is K1 plus K2, K2 plus K3, minus K2, minus K2. Equals F1, F of t, and 0. Oh no, I'll put it down here. F of t, 2f of t. Okay, so that's how you do the equations of motion. If you look in the exercises for this chapter, right at the end of the chapter, you'll see there's some 3 degree of freedom ones and so on and so forth. Like I said, it really helps the ability to go straight to the equation of motion. Okay. Now, to find the natural frequencies, we ignore the damping. Take it out. That disappears. The damping matrix disappears. We end up with just a basic system. Mx double dot plus kx equals 0. We're finding natural frequencies, so it's free oscillation, okay, not driven, and like I said, for the natural frequencies, we don't consider damping to be in there. Okay, so we've got this equation, mx double dot plus kx equals 0, and to find the natural frequencies, what we have to do is we've got to, for free undamped oscillation from a given mode of a natural angular frequency omega naught, with an amplitude signified by x, we can basically make a substitution. Okay, so if we make the substitution x is in here, then we've got, and we say it's okay, what's an oscillation. So this is my a cosine omega t. I've replaced the a with x, big X, okay, because it helps. And obviously, if you take the second derivative of this, you get an omega squared minus omega squared coming out. Okay, and that's as we saw in chapter 2. Okay, except for here, like I said, instead of a, I've got x, big xi, capital Xi. And the I signifies for mass 1 or mass 2. Okay, so make the substitution in that equation with these values, with these expressions. Okay, and what you end up with is if you do that and do a bit of manipulation, you end up with your k terms minus m1 times by, or mi times by omega squared term. The off diagonals are unchanged, and then, like I said, because we've grouped these x terms outside, you end up with a x1, x2 there, and then cosine omega t plus phi. That is not going to be non-zero, and so we can do that, divide by both sides by that, and we end up with this matrix here, which is known as the mechanical impedance matrix. Okay. So you can see that what we had here, we had our k1 plus k2, and then we had minus m1 omega squared, and that's because these terms, it's going to be minus omega squared times by those terms, okay, which is what we saw in the thing. Because when you take the second derivative, it's exactly the same as x1, except for there's a minus omega squared term. So, like I said, so you end up with this matrix times by the amplitudes x1, x2, and then, like I said, this cosine term can disappear because that's non-zero. And so we can represent that matrix, okay, as this term here. Okay. And this is known as the eigenvalue problem. Okay, the eigenvalue problem. And the eigenvalue problem is, like I said, we've got basically this equation can only hold true if x is 0 or if this is 0. Okay, x can't be 0 because that's your amplitude. So this whole bit must be 0. So how do you set up matrices to be 0? Well, basically you have to take the determinant and set that equal to 0. So that's what we're going to do. We're going to take the mechanical impedance matrix. There it is. Okay. One way to solve the eigenvalue problem and hence determine the natural frequencies is to find the determinant of the mechanical impedance matrix, Kd, and set it equal to 0. And that will result in an equation, a characteristic equation, that allows us to find the natural frequencies. Now, do you remember how to find the determinant of a 2 by 2 matrix? Have you got an idea?
Something through the lines in there of the matrix. Like add them or do you times them across?
This times this,
Yeah.
minus this times this. Yeah? AD
Okay, yeah.
minus BC. So 2 by 2, that's the way to do it. AD, it's ABCD, AD minus BC. Okay? So 2 by 2. And so that's what we do. So we take the determinant, there it is, A times by B, sorry, A times D, minus B times C, okay? And if you go through the motions of combining it all together, and you end up with a quadratic equation written in terms of omega squared, or you can replace omega squared with lambda, just to make things easier. This is clearly the quadratic equation. You've got some coefficient in front of lambda squared, another coefficient in front of lambda, and another coefficient with no lambda at all. Okay, so we look at this complicated equation. And clearly we can then use the quadratic formula to solve for the roots. Okay, so we go through that, you can find the roots. There are two values for lambda, okay, and hence two natural frequencies, omega 1 and omega 2, okay? And if you've got a 2 degree of freedom, there'll be two natural frequencies, 3 degrees of freedom, 3 natural frequencies, and so on and so forth, okay? Now I think unfortunately, oh well, here we go, you get to have a go yourself. Okay, so find the natural frequencies of the system with the following mechanical impedance matrix. And remember, if you've got a matrix, KD, the determinant is A times by D, D, minus B, C. If you've got A, B, C, D. Okay? That's the determinant. Okay, so let's have a go at this problem. Equals 0, okay? That's the first line, so that's A, D minus B, C. And then, so we've got 4 times 3, that's 12k squared. We've got minus, what do we got? Let's go for minus 8 mk omega squared minus 9, no, yeah, 9, 9 mk omega squared, okay, and then we've got plus 6 m squared omega to the power 4, okay, minus k squared equals 0. So rearranging that, we've got 6 m squared omega to the power 4, and we've got minus 17 mk omega squared, and we've got plus 11 k squared equals 0. Do we all agree? Yeah? So, now we quadratic formula, omega 1 and 2 squared is going to be minus b 17 mk plus or minus the square root of b squared, so that's going to be minus 17 mk squared minus 4a, so 6m squared c, which is 11k squared, divided by 2a. So if we multiply things out, 17 mk plus or minus the square root of 289, I think, k squared, m squared, minus 4 times 6 times 11, which is 264, k squared, m squared. Okay, 289 minus 264 is 25, that's quite convenient. Okay, and so we end up with $17 km plus or minus 5 km all divided by 12 m squared. And what we do is we cancel the squared here with the m up here and the m here, and we end up with 17 plus or minus 5 over 12 k divided by m. So omega 1 squared is 17 plus 5 divided by 12 root k upon m. So that comes out to be 1.8333 k divided by m. And so omega 1 is 1.35, oops, 1.354 root k upon m. And omega 2, I'm sort of running out of room here, let's squish some of this stuff up.
Yeah, that's very.
Omega 2 squared is 17 minus 5 divided by 12 k upon m. Well, 17 minus 5 is 12, so that's just k upon m. And so omega 1, omega 2 is simply root k upon m. So those two are my natural frequencies, or the eigen. So these are the eigenvalues of my problem. Okay. And those are natural frequencies. Okay. Now the mode shapes. The other thing that comes out when you solve the eigenvalue problem is for eigenvectors. Okay.
Sorry, really sorry. Can I see a picture of the last line? That's okay.
Yep. It's going to be on Blackboard soon, so, but that's fine. So yeah, like I said, so eigenvectors also come out, and the eigenvectors represent the mode shapes of the system. Okay, the mode shape being the relative motion of one mass and the other mass. Okay, and what we do is we take that mechanical impedance matrix. If you remember, we had x1 and x2 in here. Well, if you divide the top and the bottom by x1, you end up with 1 and x2 of x1. So this is the relative. This will be, say this. Let's say that mass 1 moved by, I don't know, 1 centimetre or 1 millimetre or 1 metre. Then x2 is going to move by a quantity multiplied by that 1. Okay, so we've said that mass 1 moved by 1 metre. Let's say that x2 happens to be, well, the x2 of x1 happens to be 1.5. Then mass 2 will move at 1.5 times whatever the 1 will be. Okay, so it's relative motion. Or it could be minus 0.5. Okay, because it's moved the other way, the other direction. And this basically, this process is ours to work it out. And what we do is we take the natural frequencies we found and we plug them into this mechanical impedance matrix to solve for that unknown, which this quantity here, which we call R. Okay. So if we set x2 over x1 to equal R, then we've got this equation, and then we take our natural frequency, and by using our values for omega 1 and omega 2, we can find two mode shapes, 1 over R1 and 1 over R2. Okay. So for example, let's take, you can start. There's two equations for one unknown, so we've got a choice. But let's say we take the top equation. So we've got this quantity times by 1 minus k2 times by R equals 0. Okay. That quantity times by 1 minus k2 R1 equals 0. So R1, quite clearly, is just that quantity there. Okay. You could do it by solving this equation. K minus k2 times by 1 plus this quantity times by R. But obviously, it's a bit more complicated. You've got to multiply R through that to solve it. But you end up getting the same thing. And that mode shape will then be corresponding to omega 1, and then you do the same thing for omega 2. Okay? A similar method is employed for R2 that corresponds to omega 2. Okay? Now she'll go again. Have a go. Omega 1. So So they were in the earlier question, but I'll give you them here. Omega 1 squared and omega 2 squared was k. Okay. So for the first one, we take the equation 3k minus 2m times by omega squared. So that's 1.8333 k over m equal minus k r1 equals 0. The m's cancel. K is non-zero, so that disappears from all three terms as well. So we end up with 3 minus 2 times by 1.8333, okay, equals R1, which equals minus 6667. So x1, so the first mode shape, which we write like this, so curved brackets but with 1 outside, is 1 minus 0.6667. Second mode shape, 3k minus 2m k upon m minus k r2 equals 0. And so we've got, again, the m's cancel, the k's disappear. We end up with 3 minus 2 equals r2, which equals 1. And so the second mode shape, x2, is going to be 1, 1. So when the system's being excited by this natural frequency, okay, the first natural frequency, you've got the two masses, one's going to be going that way and one's going to be going that way, but not as much. Okay, so you've got this sort of situation here. Okay, when you're exciting it by k upon m, two masses are going side to side the same amount. So the spring in the middle is doing nothing. Okay. So you've got out of phase and in phase as the sort of general characteristic, but with different quantities of distance because you've got different masses. Notice that the values of k and m have no impact on the mode shapes. Okay, k and m are not featured in this solution. So if you've got the same problem or same layout with different values of k and m all over the place and stuff, like I said, the mode shapes will be the same. So, I'm just debating what to do, whether to go through the example at the end of the chapter or whether I should go through this content. Right, I'm actually going to go through the example. Well, no, I can cover general solutions. General solutions is basically very straightforward. If you remember back in when we just did a single degree of freedom system, remember I told you this was the equation of motion, or the displacement for an undamped system. Any sinusoid centered around zero could be represented with this equation. Well, since there's two masses, we've now got two values like that. So x1 is basically going to be c1 times by this cosine and c2 times by this cosine, where your two natural frequencies are in there and your two phase angles. Okay, and for x2 it's going to be the same, except that you need to stick in your mode shapes as well. Okay, so you've got R1 and R2. And likewise, you can apply initial conditions to find out what those values C1 and C2 are. Okay, so there's your two equations in matrix form. Okay, and I haven't put that in there. Have I put that in there? No. But there's an exercise in the notes where you can actually go through and find out what those values are. Yeah, so with initial conditions, you can go through and find out what C1 and C2 are, and alpha 1 and phi 1 and phi 2. These are your unknowns. So you need 4 equations and 4 knowns, but you've got 2 of them there, and obviously you can take the derivative to get x1 dot and x2 dot. You apply your 4 initial conditions, you'll get values for all those 4 knowns. Okay. And if you go through the notes, you'll see that. Right, I'm actually going to skip the example that's in the notes, and I shall go to the example that we're going to do, I shall do for you. I think, yeah. We've only got 15 minutes left. With 3 degree of freedom systems, just I'll skim through that, okay? So a 3 degree of freedom system might be something like this, where you've got 3 carriages together, okay? It needs to be a semi-definite system when there's no spring, to solve by hand, this is, where there's no spring connecting it to ground. So 3 carriages on a track would be an equivalent system, okay? So there's no spring connecting it to any fixed surface, and so because of that, when you obviously use the quick method to come up with your equations of motion, and when you go through that, you've got a 3 by 3, and taking a determinant of a 3 by 3, you can follow a formula. It's a bit more complicated in terms of what all sorts of combinations. You end up with I think normally it would be 6 terms. And here we've got 0 and 0, so that drops down to 4 terms. Okay, but the problem is that once you've done that 3 by 3 matrix and found the term, you end up with a cubic equation. We are great. I can't solve a cubic. Well, no, it's a cubic. It's a quadratic times by omega squared. So one of the omega squares can disappear, which you can then solve. That omega squared that drops out, basically, is because one of the frequencies will be 0. Okay. If you remember with a semi-definite system, okay, with it because there's no nothing connected to ground, the whole thing could just move around, yeah, where there's no oscillations at all. Okay, the whole thing can move around. So you've got the frequency of 0 because it's not oscillating, and you've got a mode shape of 1, 1, and 1 because nothing's oscillating in the system. The other systems, obviously, there'll be oscillation going on, and so that omega will be a non-zero value, and the mode shapes won't be straightforward. But like I said, if you go through the notes, you'll see there's my cubic equation. Okay, so I've got an omega squared, omega squared, omega squared. So there's going to be an omega 6 going to be somewhere in there. Okay, but because that's outside, that's going to multiply through. Like I said, you end up with this setup. The only way this is true is if this is 0. Okay, which gives me omega 0 squared equals 1. This is 0, in which case omega 1 squared will be, that's for this one, omega 1 squared will be k upon n, or omega 2 squared, which is when this is 0, you end up 3k. And obviously this is that 0th mode, in a sense, which is why we call it omega 0, okay, because it's the 0th mode, and what you end up with, like I said, a 0th mode shape, as 1, 1, 1, okay? But then the other mode shapes, you can work it out. For this, you do have to, there's 2 unknowns and 3 equations. So you do have to use 2 equations to get into there, okay? So clearly for this one, we had minus R2 equals 0, so the middle mass isn't moving. Okay, but the 2 outer masses are doing this. The middle mass not moving. And then the other mode shape is where the middle mass, you've got the 2 masses outside of doing this, and the middle mass inside of moving the opposite directions. Anyway, so like I said, there's more information in those, but we're going to do this. We're going to do this example, okay? So there's 3 steps we're going to go through. Step 1 is the determining the equation of motion. So 1, EOM. So that's obviously doing that equation. So we've got M1, M2, 0, 0, x1 double dot, x2 double dot. And then we've got 3c, and then 4c, minus c, minus c, x1 dot, x2 dot. And then we've got, what's that, 3k, minus 5k, minus 2k, minus 2k. x1, x2, and then down here we've got 0 and 0. It's a free system. Are there any questions on that step? How to get from the picture to the matrix form of the equation of motion in one step? No? Okay, that's good. So step 2. Find the natural frequencies. So on mechanical impedance matrix, when you've had a bit of practice, you can just go straight from the equation of motion, this one here. So we know that we ignore the damping, so it's 3k, yeah. So this for 3k here minus m1 omega squared. Okay, this doesn't change, that's minus 2k, and then we've got 5k minus m2 omega squared. Or, in fact, yeah. Somewhere along the line we've made the assumption, I think it's in the question. But the mass is the same, okay, so we can just get rid of those subscripts. Okay, and then we've got this x1, x2 equals 0. So we find the determinant. So that's going to be 3k minus m omega squared, 5k minus m omega squared, minus 2k minus 2k. Okay, so again we go through the motions. 3 times 5 is 15k squared, minus 5k m omega squared, minus 3k m omega squared, plus m squared omega to the power 4, minus 4k squared equals 0. Okay, so we've got m squared omega to the power 4 minus 8k m omega squared plus 11k squared equals 0. So omega 1, 2 squared minus b, so 8km plus or minus the square root of b squared. So we've got 64k squared m squared minus 4ac. So that's 4 times by a, which is m squared, times by 11k squared. So that's 44. Over 2a, 2m squared. And so that equals 8 plus or minus the root 20 over 2k upon m. Okay, so that's going to be, we've got 4 plus or minus root 5 over times by k upon m. So omega 1, squared is going to be 6.2361 k upon m. So that means omega 1 is 2.4972 root k upon m. And omega 2 squared comes out to 1.7639 k upon m. (1.3281 root k upon m). Okay, so that's the two. So I'm going to make this lot. And step 3, oops. So we've got our two natural frequencies there. I'll put them in red. So for mode 1, we've got 3k minus m omega 1 squared minus 2k r1 equals 0. And so we've got 3k minus m times by 6.2361 k upon m equals 2k r1. And the k's cancel and the m's cancel, and so r1 is 3 minus 6.2361 divided by 2. So that's 1 minus 1. Okay, so x1, the first mode shape is 1 minus 1.618, so 0. And then 3k minus m omega 2 squared minus 2k r2 equals 0. So we've got 3k minus m 1.7639 k upon m equals 2k r2. K's cancel, m's cancel. R2 is 3 minus 1.76 and divided by 2, and you get 0.61. Okay, so x2 0.6180. Okay, so those are two mode shapes. Okay, that's the problem. So if we that example again will be on Blackboard. Let's go for. So this chapter, like I said, was probably revision or to jog your memory. Okay, write out the equations of motion for linear multiple degree system using a matrix form. Okay, we've done that. We have a quick method to do that. Once you've got the mechanical impedance matrix with the determinant, you'll find the natural frequencies. Okay, by finding a quadratic. Then to use the quadratic equation to solve it. And then for the mode shapes, you've got to put those natural frequencies into that mechanical blueprint, and you'll find the eigenvectors, which are mode shapes, which is the relative motion of the masses together. Okay, and we've done, and like I said, for a semi-definite system or an ungrounded system, you can actually employ this manual technique to find the eigenvalues and eigenvectors for a 3-degree of freedom system. As long as one of the masses is, as long as one of the modes is unconnected. One of the modes basically is 0, 111, sorry, and the frequency is 0. because all the masses are moving together without any oscillation. Okay? I will show you next week, or the week after, I can't remember. With MATLAB, there's a function where you just enter the function name and you can give it any degree of freedom, and it will find the eigenvector and eigenvalue. Okay, so if you've got a 5 degree of freedom system, you can use MATLAB. Okay, thank you very much.
Thank you.